Alright, here's an interesting problem that I'm going to outline for you, but then leave you to do all the work because it's like probably looks like it's super tedious. Um, the desired, let's see here. So the desired isomorphism can be written as, let's see here, we're going to send AJK to A, then beta comma gamma, then alpha plus 1 comma gamma plus 1. These are all just indices where J equals alpha m plus beta for 1, beta is between 1 and m, and then also this is implied, but alpha is between 0 and m minus 1, and k is gamma m plus delta for delta between 1 and m, parentheses, and 0, so you're equal to gamma, so you're equal to m minus 1. So what we're basically doing is you're taking j and k and you're sort of dividing them out you're doing division with remainder by m to break it up into the alpha and beta and into the gamma and the delta, and then you're using those to get your indices. And I guess I should actually draw out the picture of what this looks like. So here, I'm going to do it like this. And so just if you want to see an actual matrix, it's going to go a n m comma 1. I'm putting that I'll put commas here just to make it clear which ones is the first thing and which one is the second, because it can be confusing when you have products in there. So what does this get sent to? Let me make this a little smaller. So this is, remember, this is a m by m matrix whose entries are, and no. This isn't, it's gonna, the space we're mapping into is the space of n by n matrices whose entries are m by m matrices. So what we're going to have at the top here is we're going to have a matrix here. This is going to be A1111 all the way down to AM111, go across to A1M11, and then AMM11. So the on the bottom right hand corner, that index is like what this index would be if this were actually just a typical matrix. But the upper right hand corner tells you where this lies in the block, because what we're going to do is this is going to go all the way down, and then we're going to have over here, this is going to be AN111, they're down to AN1 M1, and I'm going to continue this, N1. Okay, so that's the first. Here, hold on. Okay, that's manageable. So yeah, so we have in the upper right hand corner, you see this block has A11, and at the bottom you have AN1. And then let's see here. So A1N11, M1, 1N. I'll just write out the rest of this just so that you can see it. Again, you can see in all of these matrices, the bottom right hand things They all have the same form because each of these is a matrix. And so it should be kind of clear. I mean, of course, we had to do this mess with like putting the A here and putting a whole bunch of stuff there and coming up with these long this division with remainder things. But it should be clear that this is an isomorphism because of the fact that what changed when we went from here to here? The only thing that changed is we put these brackets in here. Otherwise, these are both, like, if you were to remove these brackets on the right here, this would just be an n by in n. This would be an nm by nm matrix, and the thing on the left here is an nm by nm matrix. So these obviously are the same size. The J and the K formulas here just allow us to make the indices work. And remember, what is an isomorphism? An isomorphism is basically you just take your elements and you rename them. Because the bijectiveness tells you that you sort of have the same you have the same number of things in a sense, and then the homomorphism thing says that they behave the same. So if you have two things that behave that like look the same and have the same properties, then they're the same. You're just calling them something different. And so that's why it should be clear that this is an isomorphism, and you can sort of see, like, imagine, like, picture in your head what multiplication and addition would look like on the left-hand side of this, and then picture what they would look like on the right-hand side of this. And you can kind of convince yourself that, oh yeah, it would be literally the exact same thing. The only difference would be that the indices would be weird, and so you'd have to do some weird stuff to account for that. And so that's why we have these weird formulas for J and K. So anyways, I'm sure that the details, if you were to actually prove that this is an isomorphism, like prove, well, I mean, bijectivity wouldn't be too bad, because obviously, like, J and K are uniquely determined by alpha, beta, and by gamma, delta, and vice versa. And so from there, it should be clear that it's a bijection. And then as for homomorphismness of addition and multiplication, I guess that might not be too bad either. Multiplication would definitely be tedious, but it's something that you could do, maybe, if you wanted to, possibly. But I haven't been, like, assigned this. I'm not doing this for homework, so I don't want to. So if you have to do this for, like, an assignment, then that's really unfortunate. And maybe there's a slicker way to do it, but this should at least illustrate the idea that here's a way that you can actually express a matrix in the form on the left here and write it in a way that you have on the right there. So there you go. This is an outline that should illustrate how you would complete this proof.